Sequential problems are the class of problem in which the order of the features is important for making predictions. Sequential problems are commonly encountered in the following scenarios: NLP including sentiment analysis, language translation, text prediction. It is also common for time series predictions. Consider the following text prediction problem. I was born in Paris, but I grew up in Tokyo. Therefore, I speak fluent. The reason why we know the predicted word should be Japanese because we process the words as a sequence. If we remove the sequential information and only consider the words individually, we get a bag of words, and it will impact our ability for prediction. In fact, many NLP problems are sequential problems just because the languages that we speak are sequential in nature, and a sequence also conveys context. Some NLP problems also involve time event sequence. Consider movie rating used in movie recommendation task. Do you know that people's opinions on movies can change quite significantly over time? Depending on season, other people's opinion, for example after Oscar, and your own expectations. So using temporal dynamics can lead us to more accurate movie recommendations. Such sequential data make it difficult to use for a neural network. For instance, multi-layered perceptron in a convolutional neural network have an architecture constraint. The input and output must be a fixed factor. Every input given to these networks is treated independently, and they do not store any information from past inputs to analyze the current inputs because they lack memory in their architecture. To work with sequential data, the neural network needs to take in specific bits of data at each time step. This provides an idea for recurrent neural network, RNN. RNN gets their name because they apply the same function over a sequence recurrently. RNN has high-level architecture. We can break up the raw input, splitting it into the time steps. For instance, if the raw input is a sentence, we can break up the sentence into individual words. In this case, every word represents a time step. Word will be the input in the RNN. The intermediate output passed from layer to layer, and it is known as a hidden state. RNN has a memory element called states that capture information from previous inputs. So truly, in this architecture, the current output not only depends on the current input, but also on the current state, and it takes into account past inputs. Currently, RNNs are widely used. And here's some application that you might be familiar with. Speech recognition. Whether it is Amazon Alexa, Apple Siri, Google's voice assistant, or Microsoft Cortana, the speech recognition systems are RNNs. A time series prediction, any application with time series, stock market, website traffic, call center traffic, even movie recommendations, they all use RNN to predict future data. Natural language processing, applications such as machine translation, chatbots, think about Slack and Google chatbots, question answering system, they all use RNN to model dependencies. Let's look at the simple structure of RNN model. This is a folded model. In the following figure we have S state T is a state vector, and you notice it is fed back into network from the previous time step. Another important takeaway from this representation that RNN share the same weight matrices across time steps. What it means is that by increasing time steps, we're not learning more parameters, we are looking at a bigger sequence. So we have our input xt, output yt, we have weights for x, weights for y, and also weight matrix connecting the state vector of previous time step to the next one. So at any given time, The output is a function of input and weights. And you see that output at a time t depends not only on the current input and a weight, but also on the previous input, xt minus 1. RNN can be in many forms, and the appropriate architecture needs to be chosen, of course, depending on the problem you're trying to solve. One-to-many problem, when your input is single and the output is a sequence. Think about an image captioning problem where the input is a single image and output is a sequence of words explaining the image. Many-to-one, in this architecture, a sequence of inputs with a single output. An example for this architecture is time series prediction, where the next time step in a sequence needs to be predicted given the previous time steps. Many-to-many can be synchronized, direct, or indirect. So the first one, indirect or not synchronized. Many-to-many indirect is a good architecture for machine translation. And for many-to-many synchronized, an example could be speech enhancement or name entity recognition. The mathematical function of RNN is simple. Each layer T within RNN has two inputs. The input from time step T and a hidden state passed from the previous layer denoted T minus 1. Each layer in RNN simply sums up these two inputs and apply ton function to the sum. Then we output results. They will be passed as a hidden state to the next layer. What exactly is a ton function? A ton function is a nonlinear function that compresses values between 1 and minus 1. The final output uses sigmoid function, which produces an output between 0 and 1, and giving us probability for each class as a prediction. Here's some concrete example to understand how RNN handles different lengths of sequential data. Suppose we're building a simple RNN to predict whether it is snowing based on the sequential data. And here's our sentence. The weather is hot today. So what is going to be our output? Not snowing. You notice the critical piece of information, hot, came just shortly before the final output. This is a short-term dependency in this sequence. Let's take a look now at a longer sequence of text. This is a movie review. The critical words, like the movie, at the first part of the text, and appear between time steps 3 and 5, and there's a gap between these critical time steps and output time step. And you can see the rest of the text is irrelevant to our prediction problem whether the customer liked the movie or not. This is a long-term dependency in this sequence. RNN has a good short-term memory, but it does not work well with a long-term memory. So we have here what is called vanishing gradient problem. If you're familiar with the loss function, you know this function is used to evaluate the goodness of our prediction, how far all of our predictions are. And it does provide information on the accuracy of our predictions. And of course it allows us to adjust weights in each layer to reduce the loss. And the most common loss functions are mean squared error, used for regression, categorical cross entropy, used for multi-class classification problems, and a binary cross entropy used for a binary classification problem. So once we measured the error of prediction, the loss, we need to find a way to propagate loss back and to update our weights and biases. When the loss is propagated backwards, the loss tends to decrease with each successive layer. And as a result, by the time the loss is propagated back toward the first few layers, the loss is already diminished, so the weights do not change much at all. It's almost impossible to adjust a train weights of the first few layers. This phenomenon is known as the vanishing gradient problem. The vanishing gradient problem means RNN is unable to learn from early layers, early time steps, which causes it to have poor long-term memory. To address this problem, a variation of RNN was proposed known as the long short-term memory network. I suggest start with an example. How do we know that the movie rating is positive? Here's an example. The highlighted words are the most important. How about we selectively remember only important words and ignore all other words that do not really have any predictive power? So LSTM has the ability to selectively remember important inputs and to forget the rest. In addition to a hidden state, it has a cell state. The cell state is the current memory of LSTM. It flows from one repeating structure to the next, and it conveys important information that has to be retained at the moment. So, okay, how is it done? To release the information between the hidden states and the cell states, LSTM employs 3 gates: forget gate, input gate, and output gate. The forget gate concatenates previous hidden state, ht-1, and the current input, xt. Then it passes the concatenated vector through a sigmoid function. Recall that the sigmoid function outputs a vector with values between 0 and 1. A value of 0 means to stop the information from passing through, forget, and a value of 1 means to pass the information through, remember. Next gate is input. Input gate takes as input the concatenation of the previous hidden state, ht-1, and the current input, xt, and passes the concatenated vector through a sigmoid function and separately through ton function before multiplying them together. And then we compute the current cell state, ct. The output gate controls how much information is to be retained in a hidden state. We concatenate a previous hidden state, ht-1, in the current input, xt, then pass it through sigmoid function. But then we take the current cell state, ct, from the top and pass it through a ton function. And finally, we take the multiplication of those two, which is passed to the next repeating unit until as a hidden state, ht. Alright, now let's look at more practical problem to get a better understanding how the architecture works using Keras. And we use movie review data for a sentiment task with RNN. So our first layer is word embedding layer. The LSTM layer takes as input the vector representation of the words from word embedding layer, and it learns how to classify the vector representation as positive and negative. The next layer is the dense layer, fully connected layer. The dense layer takes as input the output from the LSTM and transform it into a fully connected layer. Then we apply a sigmoid activation on a dense layer, and so our final output is between 0 and 1, and it represents the probability that the movie review is positive or negative. Step 1. Word embedding. We need to make sure our word vectors must be of the same length. So we need to define maximum length to truncate long sentences or to pad short sentences with 0, as you see on your right. You have a sentence with the 4 items encoded into numbers and then 0 padded to the max length, which is 10. So you have additional 6 zeros to make length of sentence being equal to 10. Step number 2, we define a sequential class from Keras. Step 3, we add embedding layer from Keras, and we also define what our input dimension and our output dimension. So for input dimension, it's a simply number of unique words, and for output dimension, it's our hyperparameter. So for now, let's just use 128. Step 4, we add our LSTM layer, and you notice units equal 128 equal to output dimension from the previous step. We add dense layer with activation sigmoid, and this is our final layer in a neural network. So we can verify the architecture by calling summary function, and the results as you see in the bottom right.